Okay, I think I stopped the video. Okay, let's go on to 3.3 here. Okay, so this is a different method of proof. So the previous one was direct. We were doing direct proofs. Assume the hypothesis, show the conclusion. Or I say assume the if, show the then. Okay, now this is the second method of proof. And again, if you take upper level math classes, your professor is going to expect you to know how to do these different methods. They're not going to reteach everything. So direct proof, assume the hypothesis, show the conclusion, assume the if, show the then. So this is proof by contrapositive. So first we have a definition. So suppose we have statements P and Q, and we form the implication, right? P implies Q. So that's my original statement, right? That's my conditional statement. Now what's the contrapositive of this? So the contrapositive of this statement here is not Q implies not P. So this is the original statement. This is what you call the contrapositive. It's still an if-then statement. What do? You switch the order and negate both. Okay. Now remember we already talked about the converse. The converse was just switch the P and the Q. So the converse is Q implies P. Okay. So you have an original statement. Q implies P is the converse of the original, and not Q implies not P is the contrapositive of the original. Okay, now we have a nice little theorem here. Okay, so again, let P and Q be statements. Then it says, I'm not running a lot, it says P implies Q is logically equivalent to not Q implies not P. So notice what this is saying. An original conditional statement and its contrapositive are logically equivalent. So P implies Q is the exact same thing as not Q implies not P. Okay, so let's do the proof here. I'm not going to write it formally. I'm just going to use symbols here. Okay, so I'm not really writing this beautifully. Now, remember, we had this little result before that said, how do we rewrite an implication, right, in terms of an or statement? Remember, this is the same thing as not A or B. And remember, we also learned the negation of the implication was A and not B. Again, if you can remember this one, you negate to get this one. If you can remember this one, you negate to get this one. Okay, but this is one we're going to use here. So let me start with P implies Q. P implies Q. Well, from this, P implies Q, P is A and Q is B. That's equivalent to not P or Q. Okay, no problem. But, right, we have the commutative property. This is logically equivalent to Q or not P. I just switched them using commutativity. And now I claim that's the same thing as not Q implies not P. Now, why is that? Look at this right here. So use A is not Q and B is not P. So if I use A is not Q and I use B is not P, what is that logically equivalent to? The not of A, so not Q is Q, or B, which is not P. So we went from an implication to an or, then we just used commutativity, then we went from the or back to the implication. I used this twice. Okay? But going this way, A was P and B was Q. Going this way, going from here to here, A was not Q and B was not P. So we just showed the original implication is logically equivalent to the contrapositive. Okay? So why is this useful? Because sometimes proving an implication directly, like we did in the last section, is not so easy. But if you rewrite it using the contrapositive, this direct proof is easy, or at least more simpler. Okay, so that's what you keep in mind. If ever you're trying to do a direct proof of an implication that turns out to be strange or difficult or just unwieldy, consider rewriting it with the contrapositive and doing a direct proof that way. Or some other kind of proof. It doesn't have to be a direct proof, but that's all we've done so far. Okay, so that's how proof by contrapositive works. You rewrite the original statement using the contrapositive, and then prove the contrapositive. And sometimes using the contrapositive is neither nor, it's not even easier or harder than the original, but sometimes it is easier, and sometimes it's harder. Let's do an example. This is result 310. It says let x be an integer. Then it says if 5x minus 7 is even, then x is odd, okay? Nice little number theory proof here. Okay, let's do the proof. Now, before I start writing things down, we need to think about what might be the best method of proof. Okay? I mean, all we've talked about now is, direct, and now we're doing contrapositive. Think back when you took Calculus 2 and you did that whole chapter on methods of integration. Here's a problem. Before you just start using a method, what did you do? You ran through the checklist. Is it straight integration? Is it integration by straightforward substitution? Is it integration by parts? Is it partial fractions? Is it trig substitution? Is it trigonometric integral? Right? You just ran through all these different methods. And sometimes you can eliminate some just from the way it looked. And then others you may have to try it a little bit and say, oh, that's not working. Same thing when you're trying to do a proof. Right? Think about, here's a method. Is this going to work? Is this not going to work? And if you can't see, you try a little bit. So here, for example, I'm going to do scratch work over here. Let's try this with a direct proof. So assume the hypothesis. So let's assume 5x minus 7 is even. Now, what would that mean? That means 5x minus 7 is 2k for some k, and this is just scratch work. Okay, I'm trying to show x is odd. So it would make sense here to solve for x, right? Because we want to write x is 2k plus 1. Okay, not the same k here, but 2 times an integer plus 1. So if I solve for x here, okay, 2k plus 7, and I get x is 2k plus 7 over 5. And if you want, you can break up that fraction as 2/5 k plus 7/5. I hope I did that right. Okay, so here's x. Now we're trying to show that x is odd, so you need to write this as 2 times something plus 1. This isn't looking very promising. First of all, the way I've written this, if k, if k is an integer, 2/5 k is not an integer. Well, I just lied. If k is a multiple of 5, it is. I mean, suppose k turns out to be, 3. Then 2/5 k is not an integer, and adding 7/5, it's supposed to be an integer. So this is not looking promising at all, okay? Yeah. Well, you could actually factor out a 2, couldn't you? Let's actually do that instead of just my eyeballing. Right? What if I factor out a 2 here? I want to have to do a plus 1. Let's play the same game I did on the previous exercise, previous proof. 2/5 k. Let's rewrite this as a plus 1. So what do I need? A 2/5 here? Because 2/5 and 5/5 is 7/5. And now let's factor out a 2. So this is going to be k over 5 plus 1/5. Notice I didn't factor a 2/5, even though that's the greatest common factor. I factor out a 2. I'm trying to make this look like definition of odd. And notice what I have here, 2 times something plus 1. So you have to convince me to show that x is odd, that k over 5 plus 1 over 5 is actually an integer, and with the information I have, all I know is k is an integer. So why is k over 5 plus 1 over 5 an integer? We're stuck. Okay, so that was a lot of explanation, but this is what you have to do. Direct proof doesn't seem to be working very nicely here. Okay, now let's consider the contrapositive, because right now that's all we've got. So let x be an integer, that's fine, that doesn't change, that's the universal part. What's the contrapositive? Okay, so remember we have P implies Q, that's my statement there. The contrapositive is not not Q implies not P. So what does a contrapositive look like here? If x is not odd, so even, again, we're talking about integers, every integer is either even or odd, then 5x minus 7 it's not P, so 5x minus 7 is odd. So if x is even, 5x minus 7 is odd. This statement right here is equivalent to this statement right here. So if you prove this, we've proven that. Okay, so a standard thing to do, even though not everybody always does, is state the method of proof. You don't have to say we're doing a direct proof, because as soon as you assume the hypotheses in an if-then statement, everybody knows you're doing a direct proof. So, for example, here, it's sometimes helpful to say what method, we prove using the contrapositive. Just some sort of hint like that. And again, in math, we use the royal we. It's always we. We prove using the contrapositive. So what is that telling the reader? It's telling the reader, you're taking the contrapositive and you're going to prove this. You don't have to explain that. Again, the audience is everybody in our class, so everybody knows this now. So you don't have to say, we're going to use the contrapositive, and then we're going to prove that directly, and then assume the hypothesis of the contrapositive. You don't have to explain all that. But as soon as you say, we prove using the contrapositive, everybody knows you're going to assume the negation of that. And again, you don't have to rewrite the contrapositive in your proof either. Right? People can figure that out. So we're going to assume, well, let x be an integer, sorry. So let x be an integer, that's for the universal part, and assume x is even. Okay, so we're doing a direct proof on the contrapositive. Now it looks like what we did in the last section. Okay, then what does it mean for x to be even? X is 2k for some k in z. Okay, that's a definition of even. And now when we're trying to show 5x minus 7 is odd, so we need 5x minus 7 is 2 times something plus 1, where the something is an integer. Again, this is all scratch work that you should do on scratch paper. Thus, again, use a variety of words, then and thus. Thus, 5x minus 7, if I let x be 2k, that's 5 times 2k minus 7. Replace x with 2k. The reader would know when I did that because I only did one thing in that step. Let me continue. That's 10k minus 7. Okay, so in the previous problem I did, remember I wanted to get a minus 1 here, or plus 1. So that's the game I want to do. I want to get something plus 1 for the odd. So what do I need to put here to make the sum negative 7? I need a negative 8, don't I? Negative 8 plus 1 is negative 7, and there's my plus 1 for the odd. Okay, so that's the game. I'm going to continue up here, new sheet of paper. Continue with the equals. Oh, whenever, I may have said this before, whenever you're going to a new line with an equals, you put the equals on the new line. You don't put the equals here. You put it on the new line. Okay, now I want to factor a 2 out of the first two terms. I get 5k minus 4 plus 1, right? 10k minus 8 plus 1. Okay. So notice right now I have 5x minus 7 is 2 times something plus 1. All we have to say is that 5k minus 4 is an integer. And why is that an integer? Since k is an integer, because we said that over here, it follows that 5k minus 4 is an integer. Remember, we're under the assumption that we know products and sums and differences of integers are an integer. So as soon as I say k is an integer, I know 5k is an integer, I know 5k minus 4 is an integer. You don't have to write all that out. Okay, and so, hence, and again, when I write things in a string, when mathematicians write things in a string, they want you to say that, notice that is equal to that. And so what did we just show? 5x minus 7 is odd. Don't write that this is odd, because that's not the point, right? You're trying to show that 5x minus 7 is odd, so you should say it. Whenever you're doing a proof, a direct proof, or a proof by contrapositive that turns into a direct proof, say that to start with somewhere, and we did here. And you need to actually say that somewhere. So if you say 2 times 5k minus 4 plus 1 is even, you're making the reader figure that part out. So make sure you say that somewhere. And then our little conclusion, I'm just going to recopy the original. Therefore, for all x in z, again, it's universal. If 5x minus 7 is even, then x is odd. And there's our proof. Okay, now, I just tried the contrapositive and just went through it, right? Now, let's talk about how did I know this was going to work with the contrapositive? I didn't explain why. I just said, oh, okay, let's just do it, and it worked out just fine. What's the difference? Here, we started with an expression. A complicated expression is even, and then we were trying to go to x, which is simpler. right? Complicated to simple, right? That was our problem because I had to do algebra on this, and when I solved for x didn't turn out to be a nice simple expression. It turned out to be a mess. Notice here, with the contrapositive, we started with something simple, and we went to something complicated. So we started with x is even, something simple, and then when we had the more complicated expression, we could substitute in. Okay, so that's the difference. So keep that in mind when you're doing these even, odd integer proofs. Okay, so that may give you a hint on should I use contrapositive or not. Okay, going hard to simple in a direct proof may not be so easy to do, but simple to hard, I think you've got a better shot. Okay, let's do another one here. Number 17. It's the same flavor, but there's something small I think we need to do here. Okay, it says let n be an integer, and it says if 15n is even, then 9n is even. Okay, so there's our result. Now, maybe you have noticed from what I just explained, we have 15n, which is certainly less complicated than our 5x minus 7 before, but the 15n is not n. Okay, so it is a little more complicated. And notice what we're going to, 15n to 9n, it's the same level of complexity, but it's not getting any simple. It's not getting any simpler. So there's something going on here. What if I played the same game I did a second ago? Let's just try direct proof. So suppose 15n is even. That means 15n is 2k for some k. Let's solve for n. So n would be 2/15 k. No problem. But we're not trying to show n. We're trying to show 9n. But if you multiply both sides by 9, what do you get? You get 18/15 k, which is, what, the 6/5 k. And we have the same problem, right? I'm trying to show 9n is even. If I factor a 2 out of that, what do you get? 3/5 k. So 9n is 2 times something, but what's the problem? The something I cannot say is an integer. K has to be a multiple of 5 for this to be an integer, for 3/5 k to be an integer. So it's the same problem as before. Even though 15n to 9n is the same level of complexity, it's not necessarily going hard to simple. It's going, hard to itself. But we're still running into that problem. But again, you got to do the scratch work. Now the problem is, what if we do the contrapositive? What if we do the contrapositive here right now? Okay, that would be 9n odd implies 15n odd. Right? You switch and negate. So if we do the same thing, 9n is 2k plus 1, solve for n, and then take 15n, it's going to be the same mess we had before. You could work it out yourself and see. So if I try direct proof, we get a mess. If I try the contrapositive, I get a mess. So here's what we're going to do. I say to prove 17, first we need a lemma. So a lemma is a small theorem. A lemma. Okay, let me write it down. Let n be in Z if 15n is even, then n is even. Okay, so a lemma is a small theorem. Typically in mathematics, when you'll see a sequence of lemma, and then you'll see a theorem with a proof. And in the proof, they refer back to all the lemmas. So a lot of times, a lot of little lemmas will break up a long proof, right? So you'll say in the proof of the theorem, assume so-and-so. By lemma 1, we get this. And then this, by lemma 2, gives us this. By lemma 3, gives us this. And you get to the end. So the proof of the theorem is short. The lemmas are doing all the work for you. So that's what I'm doing here. Okay, now you may say, well, how in the world did I come up with this? Well, what was my thinking here? Going from complicated to complicated wasn't working. And if I do the contrapositive, it's complicated to complicated. It wasn't working. Notice what my lemma has. I have complicated to something simple. I went down to the single variable, just like we had success in the previous example. Okay, so assume, and again, well, just pick, if 15n is even, n has to be even, just pick some examples to figure that out, right? If 15n is even, try some odd numbers for n, and it doesn't work, right? So again, you make up the lemma. So you want to come up with something that's complicated to easy, and then you just have to come up with something and then try values to figure out what it is. So let's do this proof. Okay. Now notice I'm going complicated to easy. And that didn't work in that previous problem. I want to go easy to complicated. So notice if I take the contrapositive here and prove the contrapositive, it'll be easy to difficult. So we prove using the contrapositive. Again, that's telling the reader I'm not doing a direct proof, so they'll understand my first sentence. And again, if you need to work all this out, right? P implies Q. How does the contrapositive work? It's not Q implies not P. So assume n is odd, right? The negation of this. And I need to show 15n as odd. Okay, then n is 2k plus 1 for some k in z, right? If n is odd, that's a definition of odd. Now I'm interested in, okay, no, I should have written this over here for me, right? So I'm trying to show n odd implies 15n odd. See, I lost my train of thought because I didn't organize the information for myself. So on scratch paper, I'm writing the contrapositive. N is odd implies 15n is odd. Okay, so I assumed n is odd. N is 2k plus 1 for some integer k. I'm trying to show 15n is odd. Okay, so 15n is 15 times 2k plus 1. And again, I'm trying to get 2 times something plus 1. So this is 30k plus 15. But I want the plus 1, so I'm going to steal a 1 from the 15. So that's 14 plus 1. Okay, good. And now factor a 2 out of the first 2 terms. Okay, so I have 15n is 2 times something plus 1. All we have to do is explain the something is an integer, which it is. So since k is in z, it follows, or we conclude, I keep saying it follows, you could say we conclude that 15k plus 7 is an integer, and we just showed 15n is odd. Right? 15n is 2 times an integer plus 1. Therefore, I'm writing the summary here. If n is in z and 15n is even, then then n is even. I mean, it's nice to n is even. It's really nice to do a conclusion statement in a proof by contrapositive because you assumed, right, this hypothesis and that conclusion. So it's nice to write the conclusion of what you actually proved. I know we proved that, but right, we're trying to show that. So that, I didn't write the conclusion here. I didn't write that as my conclusion. I wrote what I was trying to show as the conclusion. Okay, so now we have this lemma. So we can use the lemma. Okay, and now we're going to go back to the proof of my original theorem here. Okay, but I can use my lemma. Again, what does my lemma do for me? If I start with 15n, it gets me to simple, complicated to simple. Okay, so now let's go back to the proof of this number 17 here. Oops, proof. Okay, now notice in the hypothesis of my lemma, I have 15n is even, which is the hypothesis of my theorem here. So I'm actually going to now prove 17 directly. Okay, because it's simple, it's complicated to easy. So if I start with complicated, I can go to easy. Okay, so let's do the proof. So let n be in z and assume 15n is even. Okay. So you say, why is this problem in this contrapositive section when I'm proving this number 17 directly? Because to prove this, I used a lemma and it used a contrapositive. Okay, let n be in z, assume 15n is even. Well, by the previous lemma, right, this one right here. If there's actually a math paper or something, they would be numbered lemma 1, lemma 2, or something like that. We conclude that n is even. Okay? So all the work we just did in our proof of the number 17, we went from 15 is even to n is even in one step because we did all the work already. Okay? Okay, so now what's the definition even? Thus, n is 2k for some integer, or some k in z, I could just say that. I said N is Z there, let me be consistent. For some K in Z. And now what are we trying to prove? We're trying to prove 9N is even. Hence, 9N would be 9 times 2K, right? Our N is 2K. That's 18K, just to save a step, even though it's no big deal. I think most people would follow me if I just did that, right? 9 times 2K is the same as 2 times 9K. I think most people would be okay with that. If you want to put 18K here in between, that's fine too. Okay, now why did I stop there? I'm trying to show 9N is even. I got 9N is 2 times something. And again, I need to explain that's an integer. So since K is Z, I said we conclude up there, so I'll say it follows again. It follows that 9K is in Z. And we just showed, right, we have 9N is 2 times an integer, and 9N is even. Okay. Therefore, I'm just writing conclusion. If N is in Z and 15N is even, then 9N is even. And there we go. Here's our proof. So I did this with a direct proof, but I needed the lemma to explain how to go from complicated to simple. So we did so in this proof of number 17, I did a direct proof, but I used a lemma in which we proved it with a contrapositive. Now let me remind you here, I mentioned this the other day. Right here, right, okay, we started with 15N is even, and then from that, we got N is even, right, from our lemma, right? And then I said N is 2K for some K. Now here's what students will do. They'll say, oh, okay, so instead of doing this right here, they'll say, since N is even, 9N is even, since the product of an even number and an odd number is even, okay? Again, I mentioned the other day, don't use equivalent level results, okay, in your proofs. I mean, everything here, you could figure out, oh, the product of two evens is even, and an even times an odd is an even, and an odd times an odd is an odd. But I don't want you to use that in the proofs because we're practicing using the definition of even and odd. So I want you to actually work it out, okay? Don't use equivalent level results. We're trying to show if something's even, something else is even, and then you're basically saying, oh, if something's even, then if N is even, 9N is even. Okay, you're using basically something at a result at the same level of what we're trying to prove. So don't do that. Okay, now lastly here, it says, I have a note here. Okay, now we've been doing proving implications. Now how do you prove P if and only if Q? Now remember what that meant. That meant P implies Q and Q implies P. So to prove an if and only if statement, the biconditional is true, to prove it, what do you have to do? You have to show prove if P then Q, and you also have to prove if Q then P, okay? Now keep in mind, you may prove if P then Q with a direct proof, and you may prove Q implies P with a proof by contrapositive, okay? Or you may prove them both directly. You may prove them both using contrapositive. So just keep that in mind. When you do this one, the method to prove this one and the method to prove this one could be two completely different methods. Okay, so you just have to keep them in mind. They could be the same, but they may be different. So just because you do direct here doesn't mean that the direct is going to work there. So just keep that in mind. But remember, to prove a biconditional, you have to show the implication both directions. Okay, if it's just a straightforward if-then statement, you don't show it both directions, right? Only prove the direction that you're trying to show. Okay, so that gets us through that section.